This session we'll be looking after different types of connections, okay, that a three-phase circuit generally is made in order to get different voltage levels, different potentials, different currents, okay, ultimately different power. Okay, so first thing is, any three-phase production unit will have three phase quantities. Okay, first quantity is phase current. Okay, as we all know, current I is equal to V by R. This is a general formula according to Ohm's law. But according to this, a phase current is current that is flowing in one phase. Okay, generally that is given as I, capital I, phi. Similarly, line current is given as I, capital I, and L, line current. Phase voltage is V phi. Similarly, line voltage is VL. These are some notations which you have to remember while dealing with any three-phase circuit. Any three-phase circuit, if you want to remember all these currents and voltages, so these are the notations generally used. Okay, so we are ultimately, see, look at this equation. We are concentrating upon I and V, but R will be your load. Okay, what kind of load and all we'll discuss in the upcoming slides. So coming to the voltage, phase voltage and line voltages. Phase voltage is measured between neutral and any line. So line to neutral voltage is called as phase voltage. As I said, in case of three-phase circuits, okay, we have different types of connections. This is a 4-line three-phase circuit. We have neutral on top. You have phase 1, 2 and 3. Generally it is represented as 5, 1, 2, 3. So if we measure the voltage in between any two lines, that is neutral and one phase, or neutral second phase, or neutral third phase, that is called as phase voltage. Okay, this is called as phase voltage. Similarly, line voltage is voltage that is measured in between any two lines, that is phase 1 and 2 you can measure, that is called as VL, line voltage. This is generally in the order of 230 volts for our home. Okay, line to neutral, okay, line to neutral voltage is 230 volts. Coming to line voltage is 440 volts. Okay, 400 to 440 volts. Similarly, what is line current and phase current, we can have a look. Line current is basically a current in each line of source or load. How to connect loads and all we can have a look. Line current is the current that is existing in one line. For example, neutral will not have any current because neutral lines are basically zero current things. Okay, lines will have current IR, which is R, phase R, I blue, IB, I Y, RYB or RBY, anything is fine. Okay, so we have three currents in case of a three-phase circuit, that is to line current, three line currents. Okay, each line we have. So generally, what is the line voltage? We have seen line voltage is 440 volts. It's a huge value. Similarly, currents also will vary. Okay, but for household, even if you use three phase or like whatever phase that is required, currents will remain mostly common. Okay, which is a high value. Similarly, phase current that is existing in each phase of source or load. Okay, we have taken phase voltage, no, generally this phase current is 5 amps. All your household things are connected with 5 amps only, right? So that is your phase current only. There should not be any fluctuations in the phase current. It should be uniform. What happens if you have fluctuations? There will be a problem. That problem would end up with burning or maybe fire accident or something. You have to maintain it. Okay. Second thing is interconnection of windings. Any three-phase circuit will have two types of three-phase connections. Okay, two types of three-phase connection. First one is star denoted by Y. Okay, circuit will look like a Y configuration. Similarly, delta, there are only two configurations. The very first configuration, as you have seen, which is star connection. In this method, we have interconnection of similar ends of your load. Similar ends of what? Your load. What kind of load it is? This load could be resistive load, this is a resistive load, inductive load, okay, make a note, inductive load, resistive load, or capacitive load. Okay, generally this load is represented by a terminal Z, which is called as impedance. Okay, impedance, Z is impedance. How to calculate Z and all we will see in the upcoming classes. Okay, can you give one good example of resistive load? Electrical heater. Electrical heater is a resistive load. Can you tell some capacitive loads? Any capacitive loads in your fans? Okay, in your no, that is not a capacitive load. Chargers are never capacitive loads. That is also kind of inductive loads only. Don't consider capacitors as capacitive loads as your mobile chargers. That is very wrong. Okay, so there will be in your mobile sorry, in your ceiling fans, any kind of fans, there will be a capacitor. Okay, in your tube light systems also, in the choke, beside choke you have some capacitor. Okay, so these capacitors are called as capacitive loads. The impact of these capacitive loads are a bit low only, but they will serve for another purpose also. Okay, they will serve for, so you have inductive loads. Capacitive load is some capacitance basically. Okay, it is used for rectifying your different various parameters in the electrical circuit itself. Okay, so this capacitive load especially is used to start your motor, start your fan. These are called as starter circuits. Okay, it is very less, you should not concentrate much upon capacitive loads and all. Second thing is inductive load. Okay, inductive load is your motor, okay, mixer grinder, all the things which will rotate is an inductive load by default. It will have some coil. Okay, so the impedance okay, is converted to resistance in common. Okay, so the impact of resistance is given by R. This is very important thing, R. Okay, XL, this is called as inductive impedance. Inductive impedance. XC, capacitive impedance. Okay, this is just a simple resistance. Resistance will not have any impedance. It's a pure resistive load. Okay, so these are the different, a combination of all these things will call as Z. Okay, or impedance, simple impedance, cumulative impedance. So in this, the similar ends of all these loads are connected to three coils. It could be a finishing end. Generally, this finishing end is denoted by N. Okay, any star connection will have 4 wires. Keep this in mind. 4 wire system. One is neutral and 3 phases. How did you got the neutral? By joining the similar ends. Okay, first thing, let us check how does this star connection or star configuration looks. Okay, look at this figure. You got one end of a coil. Okay, this is one load, this is another load, this is another load. All these loads are connected together in order to get a common node called as N. This is called as a neutral node or neutral end point, right? So between IR and neutral, what kind of voltage you can get? It's a phase voltage. Okay, phase voltage, which is 230 volts. Similarly, between Y, between coil Y or a load Y and neutral, whatever you get is again 230 volts, which is a phase voltage. Similarly, between neutral and B is blue wire. Okay, in general terms, whatever you get is 230 volts. Clear? And current that is flowing through this load, okay, okay, is called as IR, IB and IY respectively. Okay, so according to Kirchhoff law you might be studying in your electronic circuit solving and analysis, the algebraic sum of currents that are joining at a node is equivalent to 0. According to Kirchhoff current law, the algebraic sum of the currents that are joining or entering and leaving a circuit will be 0. That is, we have a vector sum of 0. In this case, if the 3 voltage is said to be balanced load, if the 3 phase circuit is considered to be balanced load, this is one type of inductance ZR. I'm just taking ZY. This is one load. This is ZB. If ZR is equivalent to ZY is equivalent to ZB, then this whole circuit is said to be a balanced load. Okay, balanced symmetrical load. Symmetrical means all the Z's are equal, right? All the Z's are equal. Similarly, another condition that will satisfy balanced condition of your circuit or a star connection is, star or Y connection is, the algebraic sum of sigma I, okay, that is equivalent to IR plus IY plus IB, which is equal to 0. Is this thing clear? Okay, so now we will take voltage, whatever voltage that is obtained. Okay, now we have seen a phase voltage. Let us check the line voltage. We have already checked what is the phase voltage and what is the line voltage. Clear? Measured between neutral and the line is called as phase. Between any two lines it's called as line voltage. Just keep this thing in mind. Okay, what is this line voltage? We have VR, okay, that is R, and Vy, okay, or the line Y between whatever these two lines, okay, will contribute a voltage called as VRY. Similarly, Vy by Yb between Y and B. Between B and R it is Vb. Clear? These voltages are 440 volts. Right, these voltages are 440 volts in general. Phase voltage is 230 volts. Clear till now? Let us check what is the output voltage. Okay, output voltage, right? Whatever the current that is flowing through is called as, again, line current IR, IY and IB. Okay, here neutral is not considered for measuring line voltages, right? Now, so according to this different phases of the things, we got ER is equal to EY is equal to EB is equal to E phase. That is, here also all the three voltages should be 440. If there is any change in the voltage, then the circuit is said to be unbalanced circuit, right? Coming to the thing, we will make some vector diagram. In vector diagram, what we are planning to do is, it is drawn in between current and voltage. Okay, first, as we know, ER and EY are having an phase angle of 120 degrees. Okay, 120 degrees. The resultant is IR. When you make these two things, the resultant is IR. That is indicated by symbol phi. Okay, line voltage between VR, okay, and the line, that is line 1 and line 2, the vector difference is ER and EY. The vector difference of VR, that is line 1 and line 2's vector difference is ER and EY. Similarly, line voltage VYB, this one, okay, that voltage between these two things, line 2 and line 3 is called as VYB. It is vector difference of EY and EB. It is also 120 degree apart. Okay, right. Similarly, we have the third voltage VBR, that is 3 and line 1, we have vector difference of EB and ER respectively. Clear? Now we'll make the differences between all these things. So we have seen one particular configuration which is star. Now we'll switch to delta, then we'll check what is the difference between these two. Okay, we have seen this thing, how the loads are being connected. In star, the loads are connected in series with your coil. Okay, in series with your coil, that means a coil is connected in series with the load, it will have a common point. Similarly, one coil is connected with another load. This is the generator end, this is the generator end, this is your line, whatever the power lines that comes to your home. Similarly, you have one more load that is connected. So all the end terminals of the loads are connected to a point M, which is called as a neutral. As I said, that is the equivalent current, that is sigma I is equivalent to 0. This is what we have learned with star connection. Similarly, how the loads are connected in this format. The biggest advantage is you will have a neutral connection. Okay, you will have a neutral connection so that you can take 230 volts. But in case of delta, okay, in case of delta, it is not possible to have that sort of connection. Okay, just have a look. 3-phase voltage system RYB. Okay, all the loads are connected to common point. This is your neutral. This is your neutral, right? Similarly, in industrial side, you don't require a neutral. The machines itself are what do you say, 3-phase system. They don't require neutral. But in our household, we require neutral because we require 230 volts, right? Practically, it is not always possible to make a star connection in domestic load balance. You cannot balance your household systems because different ratings will be there. Your TV rating and your fan rating are different. Your mixer grinder rating and your whatever the other appliance ratings are different. You cannot make it. It's not possible. Okay. So this whatever the neutral that we get, because there is physically no neutral connection here, but we are making the neutral by assuming sigma I, which is equal to 0. Clear? Now this neutral is called as floating neutral. Okay, where the voltages across the 3 loads are adjusted themselves. Okay, so in order to avoid this, we use a 4-wire system. 4-wire system, as I said, this is the issue if we use a 3-wire system, right? Delta connection. In delta connection, what happens? Okay, whatever the coil that is connected with the load, it is a direct connection. It will give you only 440 volts. You can connect in between 2 lines only. There is no neutral position because it's a closed loop circuit. Okay, it's a closed loop circuit. So whatever the voltage that is generated between R is VR. Okay, or in simple terms we call it as VRY, that is voltage between R and Y. VYB, VRB. So all are equivalent to 440 volts only. Okay, right. So at the end of each phase we are connecting one load, right? At the end of each phase only we are connecting one load. At the end of each phase only we are connecting another load. Okay, the biggest problem is when you are connecting like this, whatever voltage you get is 440 only. It is not possible to get 230 volts, right? Similarly, voltages and currents, how they are related. Okay, in star connected systems, okay, in star connected systems we have already discussed how does the voltages will be there. Okay, we have voltages as VRN, that is between R and neutral, VYN between Y and neutral, VBN between B and neutral, that is blue and neutral. Okay, so whatever the voltage we get, we can split, right? We can split. Here there are 2 combinations possible, that is you connect it to 230 volts by connecting in VRN, okay, YN and Bn configurations. Similarly, we can get one more voltage, that is VRB also it is possible. Okay, Vyn is also possible. Not N, Vy Ry is also possible. Okay, so this voltages are 440 volts. So two combinations are possible in star connection. That's a major advantage, right? Now in three-phase system, we have already studied all these things. What is a phase voltage, what is a line voltage, and what is a three different phase voltages and all. The biggest advantage is you get, with respect to phase, we get Rn, Yn and Bn. With respect to individual lines, we get line voltage also, that is Ry, that is between R and Y. Similarly, B and Y. How do you calculate these voltages? Let us assume Vry, voltage between R and Y. How it can be splitted up? Okay, Vry is splitted into Vrny. We can consider neutral. Neutral is actually 0. Vrny is nothing but Vrn plus Vny. Okay, what is Vrn minus Vyn? When you just take it that side, right? When you are equating, minus voltage, right? So that is Vrn plus of minus Vyn, right? One is both are exactly in opposite directions. Okay, the resultant whatever we get is the third part. Okay, where here Vry is equivalent to 2 into Vrn into cos 30. That is the resultant what we got, right? Or V line voltage is 2 into Vph into under root 3 by 2. So whatever the line voltage that we get is under root 3 times of V phase. This is in case of star or Y connection. VL is equal to under root 3 V phase. Similarly, IL, that is the line current, is equivalent to I phase in case of a star connection, where line voltage is actually under root 3 times of Vph. What is this under root 3? How much is the value? How much is the value? Can somebody tell? What is under root 3?
1.732.
1.732. So under root 3 is 1.732. So it is one line voltage is 1.732 times of phase voltage. Okay. Similarly, line current is equivalent to phase current. In star, you just remember these two things. VL is equal to under root 3 Vph. Similarly, IL is equal to I phase. Let us move on to delta connection. This is like the phasor diagram. Okay, you can have a look. Right. In delta connection, whatever we get is what voltage? What is the voltage between R and Y? Line voltage only. We got only line voltage, which is equal to 440. Only one combination is possible, right? Where the current that is passing through RYB is actually the current that is passing through the coils of generator. It's a direct current. That is IRR. Whatever current passing through this coil will be given to the load. Similarly, whatever the current that is passing through this coil is given to this particular load. Whatever the current that is passing through the Y coil is given to this particular load. That means all the currents are equal, or the phase currents. Currents that are passing through individual coils are basically phase currents. All currents are equal. Okay. Let us check what is happening with the delta connection. IR is nothing but, okay, we got, let us check what is IR alone. Okay, it is actually passing through two things like this. I'll just erase it off and just let you understand more. So it is passing in this fashion. So IR is nothing but whatever the voltage that is generated between BB coils and RR coils is IR, right? From the figure, it is much vivid that IR is equal to the current that are the difference between IRR and IB dash B or BB. Okay, here the current equation is given by 2 into I phase cos 30, which is under root 3 I phase. Okay, under root 3 I phase, where the line current or the current that is passing through line R is under root 3 of I phase, whereas voltage is equal to, or the line voltage is equal to V phase, right? Voltage is equal to V phase. Okay. Right, is this thing clear? How to draw this vector diagram? Do you want me to explain? If you want, I can. As I said, it is the difference between RR and VB. Okay, yeah. So let us have some differences between star and delta. Okay. First thing, three phase voltage will have see a specific values for line and line currents. It is always, it's a normal practice. The currents in any phase can be determined by dividing the phase voltage and by its impedance. Okay, let us check with some example problem. A 400 volts three phase supply is connected across a balanced load. Keep this in mind, a balanced load. That means all impedances are equal. Z1 is equal to Z2 is equal to Z3. Okay. What is the kind of circuit they have taken? Both the connections we have to determine what? Okay. In the problem it is also given that it is consisting of 32 ohm resistance, R value is given, and 24 ohms inductive reactance. Keep this in mind. Inductive reactance is given. That means Z is equal to R plus J omega. Okay. But whereas Z is equal to 32 plus, what is this? 24. Okay. 24 under root whole square. Z square plus. Okay. This is what generally it is in practice. Let us check how it can be solved. So what we have to measure is determine the current drawn from the power mains if three impedances are connected in Y and delta. This is the question. Generally it will be given in this form only. First we have to calculate what is Z. As I said, Z is equal to R plus J omega. Okay, let us check. What is this omega here? Jx. Jx. What is this x? XL. In the first very beginning I have told it is an inductive load, right? It's an inductive load. Okay. How to remove this J? J can be removed by rooting and individual squaring, right? Rooting and individual squaring. So that is 32 square plus 24 square under root. What is the value? Can you determine? What is 32 square? 1024 plus what is 24 square? 576. What is the value? 1024 plus 576. What is the value?
1600.
1600. Under root will be 40. Isn't this clear? So the answer is 40 ohms. You have to be very specific. It is 40 ohms. Now let us start with Y connection, that is the star connection. In star connection, what is V phase and what is, or V line or V phase, whatever it is, I phase? Can you tell? The previous example we have checked it very clearly. V phase is under root of, or like V line is equal to under root 3 of V phase. Okay, that is what it will be given. V phase is, just a second, V phase is VL by root 3, or VL is equal to under root 3 into V phase. The phase voltage is given as how much? 400 volts. Okay, 400 volts. That is 400 divided by the line voltage is given as, not the phase voltage. Keep this thing in mind. Phase voltage is given as, okay, 400 volts. It should be very clear. right? That is 400 divided by under root 3, which is 1.5 something you will get. So what is the value for that? You just take out that value, okay? But what is I phase? As we know, V is equal to IR. Here R is equal to Z, okay? I is equal to V by Z, right? I is equal to V by Z. Using that formula, we got V phase by Z. Z is already known, which is 40 here. So 400 divided by under root 3, that is 10 by under root 3 amps, which is 5.78 amperes. Okay, V phase voltage directly you will get 400 by under root 3, right? Any other doubts in this?
Sir, question already solved, sir.
Okay. I repeat the question for your sake once again. Now let us start with the delta configuration. In delta configuration, as we know, V phase is, or the voltage in the phase is equivalent to the line voltage itself, which is 400 volts, whereas I phase is V by Z. I phase is not the same thing, okay? I phase is not the same thing, right? It is I line divided by under root 3. This is what I phase, okay? It is given as like this: IL is equal to under root 3 I phase, right? But we are planning to find out what is I phase directly, that is V phase by Z, 400 by 40, which is 10, okay? 10 into under root 3, which is 17.32 amps. Now, which connection out of these two problems, which connection is more suitable when you have a high amperage requirement, when you require more current at the beginning? Which type of connection is preferred? Delta connection. Here
Delta.
amperage is more, right? Similarly, which type of connection is suitable when you require two types of voltages? Y connection or star connection, right? Star connection is suitable when you require low current at the beginning and voltage to be of two types of voltages. Similarly, delta connection is suitable for high amperage when the current requirement is very high at the beginning. But the problem is you don't have two voltages split up here. You don't get multiple voltages here, right? So let us calculate power in case of a three-phase system. Okay, power is a product of, power is denoted by P. Generally in terms of watts it is V phase into I phase. We are considering only phases, not the lines, right? Into cos phi. In any case of alternating current circuits, AC circuits, this cos phi will be there, right? This is the phase angle, which is 120. So cos 120 is how much? .814. So your phase and line current, phase current and the phase voltage should be multiplied 0.814 times in order to get the power in watts or kilowatts, right? So the total power that is consumed, okay, in a balanced load, keep this in mind. What is balanced load criteria? Z1, Z2, Z3 are equal, okay, which is 3 into 3 times the power, okay, which is 3 times the power. If one phase is considered, this is the thing. If 3 phases are considered, 3 into P1, that is 3 VPH IPH cos phi. For a star connected system, how does this power will vary? Let us have a look. In star connected systems, we all know that V line or the voltage in the line is under root 3 times of phase voltage and IL is I phase, okay. Similarly, power will become 3 into VL divided by under root 3 into IL cos phi, that is under root 3 VLIL cos phi. This is the final equation for power. Similarly, for delta configuration, it is, we all know VL is V phase and IL is under root 3 of I phase. For delta connection also, the power will be the same thing. Okay, so any connection you take, the ultimate power that should be equal. Okay, in a balanced load, the power should be equivalent. In a balanced load, the power that is totally consumed by any connection, star, delta, or whatever the connection is, it is equivalent to under root 3 VLIL cos phi. This is the total power in any circuit. Okay. So what is this total instantaneous power? It is a combination of power that is generated from A phase, B phase and C phase, right? What is average power per phase? It is either PA or PB or PC. That is the average power, right? That is the average power. Okay, this is a very important point. In three-phase circuits, in any three-phase circuits with balanced load such as three-phase motor, okay, there is no variation of power at all. This is the reason why driving heavy mechanical loads we generally prefer with three-phase motor rather than a single-phase motor. That means the power is uniform. There is no variation of power, right? Okay. So let us check the example number 2 in order to find out all the equations that till now it's been discussed. That is, what is your power factor, what is your total power in case of your all the AC circuits that we have checked till now. Okay, in the example 1, whatever we have checked now, so whatever the power related things and all, we can do it in this example, right? So the question is given like this, that is a 400 volts 3-phase supply. Keep this in mind, a 400 volts 3-phase supply, it is connected to a balanced network, that is Z1 is equal to Z2 is equal to Z3. This concept you have to remember till end of this 3-phase circuits. Okay, it is consisting of two things. One is 20 resistance and 50 inductive reactance. R is 20, XL is 15. Okay, so if three impedances are connected in star and delta, in each case, in star case we have to define what is line current, and in delta case also we have to define the line current and the other things. We have to define what is power factor. Power factor is cos phi. Okay, how you will define this cos phi? It's a ratio of, now the total power in the previous example we have seen, no? What is the total power? Can somebody tell? Under root, what is the total power? You can have a look of this. Under root 3 VL IL cos phi. This is the total power. We have to calculate total power in case of this thing also, right? For star connected load, okay, what is the first question that is asked is, have a look, what is the first question that is asked? Line current, IL is asked. Okay, IL is equivalent to I phase in case of a star connected network. But what is this IL? We have to find out from this equation, that is V phase is equal to VL by under root 3, where it is equivalent to 400 by under root 3, which is 230 volts. This is what we get to our homes, 230 volts. Okay, from this calculation only they have made this typical household current, household voltage, right? Similarly, Z phase, which is 20 square plus 15 square under root, that is R square plus XL square under root this thing. You will get 25 ohm, right? So we got V by Z. You got what is what. Now we will find what is line current. It is I phase. I phase is equal to V phase by Z phase, which is 231 divided by 25. 231 divided by 25, which is almost 9.24 amperes. Clear? Similarly, they have asked one more thing, power factor. Power factor is nothing but it is a ratio. We have already discussed in the previous class also. It is what? The ratio of the real power and instantaneous power, or the real term, which is resistance, and Z, right, which is reactance. So that is R by Z. Z is how much? 25. R is given as 20. So 20 by 25, which is equivalent to 0.8. Okay, 0.8. Why it is lagging? How will you define if it is lagging or leading? This concept we will discuss at the end of, almost end of this what do you say this chapter. Okay, don't mention it as of now. 0.8 is the value. Now the next one is power, which is equal to under root 3 VLIL cos phi. Okay, that is under root 3 400 into 9.24 into cos phi. Cos phi is this thing, right? Cos phi is 0.8, which is 5,000 and almost 120 volts. That is 5.12 kilowatts. That's the total power in case of a star connected network where the loads are balanced. Z1 is equal to Z2 is equal to Z3. Okay, under standard load conditions. Next one is for delta connection. What is V phase? VL is equal to V phase, IL is equal to under root 3 I phase. Clear? So VL minus V phase is equal to, sorry, it's not. VL is equal to V phase. It's a straight away answer. So what is I phase? V phase by Z phase. 400 by 25. We have already got 16 amps. We already know in delta connection current rating will be more. In the previous case current rating is how much? Hardly 9 amps. But here it is 16 amps. We got a larger current. Okay. So IL is equal to under root 3 I phase, which is 27 amps altogether. Even the phase current is also more. Line current is much more. Line current is much more. It's very huge. Okay, almost double. Not double, more than 3 times. Similarly, it is the same power factor. No need to do it once again. So the power also should be remain the same, which is 5 point, sorry. What is the power value here? VL IL cos phi, which is equal to 5.12 kilowatts. Just check the power here. 15.36 kilowatts. Is the load balanced in case of delta? No. Load is not properly balanced in delta. That's the reason you are consuming more power. Right? Load is not balanced. The power consumption has become 3 times more. Have a look. 5 kilowatts in case of star connected network, and delta connected network it is 15 kilowatts. Okay, so it has become 3 times. So delta connection is for sure it is a power hungry network, but you cannot apply it everywhere. Okay, let us check some common differences between both. Similar ends are joined together in order to get what? Neutral. Dissimilar ends are joined together. Okay, dissimilar ends are joined together. V line, that is line voltage, is under root 3 times of V phase. IL is I phase in case of star. VL is equal to V phase. IL is equal to under root 3 I phase. Neutral wire is available. It's not available here. 4 wire 3 phase system. Okay. 4 wire 3 phase system is not possible. Only 3 wire system is possible. Both industrially and domestically we can use. Only industries can use it. Okay. By earthing the neutral wire, relays and protective device can be provided for alternator safety. It is not possible in this case. Okay. So before going to this, I'll conclude the class.